This video is sponsored by Brilliant. More about them later. Hi there everyone. In this video, we are going to be testing the latest and greatest motors for FPV drone racing. And in drone racing, the difference between places can be decided in fractions of a second. So pilots are looking for motors with the maximum performance and maximum efficiency to give themselves an edge over their competition. We're going to be looking at motors from T-Motor, Axis Flying, 533 and RC Power to see who makes the fastest motor. In this video, I'm going to be taking you through the key features of these motors on the bench, and then we're going to be looking at some super detailed motor testing results so that we can decide who is going to be the winner for today. It's a lot to cover in one video, so let's not waste any more time. Let's get straight to the lab. Alright, so here I have all of the motors we're going to be testing today on the bench. And as you might expect, there are more similarities than differences in all of these motors. So I'm going to cover the similarities now, and then we're going to dive into the unique features of each of these motors. So all of the motors feature thick single core windings, high-grade aluminium bells, steel flux rings, thick N52 magnets, and an aluminium base which has had as much weight stripped out of it as possible so that these motors produce the maximum amount of power for the minimum weight. Shafts of these motors are typically titanium or high-grade steel, and they use generally Japanese imported bearings. All of the motors feature O-rings in the underside of the bell to cushion the top bearing against impact to help prolong the life of the bearing and keep it running smoother for longer. There are two main designs of the motors. We have motors that are using a two-piece bell design, where you have an aluminium top part of the bell bonded to the steel flux ring there. And that's an example. This T-motor has this two-piece bell. The RC Power motors feature a unibell design, which means that they have the aluminium bell extending down over the steel flux ring, just a very thin kind of sheath going around that steel flux ring. That helps improve durability and reduce the risk of the bell slipping down, which can be an issue with some two-piece bell designs. Although of course that does depend a lot on the manufacturing, and I wouldn't expect any of the motors that we're testing today to have any issues with slipped bells. So now coming on to the unique features of each of these motors, let's start with the T-motors. We have the F60 Pro 5 and the F40 Pro 5. So this is the fifth generation of these motors, and T-Motor promise more performance and even better durability with this design. We have two different sizes. The F40 is a 2306 and the F60 is a 2207. But other than that, all the features are pretty much identical. We have a couple of different KVs of each of these motors, and we're going to be looking at the effective KV on the test results later. We have this heads-up FPV 533 motor, which is Evan Turner's motor. And again, this is a two-piece bell design. This has a recessed bottom bearing to help save even a little bit more weight. But when you recess the bearing like that, the two bearings end up close together in the motor, which slightly reduces the durability to these kind of bending loads, torsional loads that you might get if you crash hard. The interesting thing about this motor is that it comes with an MR30 connector. So you can actually take the motor off the drone without needing to desolder it. That's a really nice feature for racers. It does add a couple of grams. So when I weighed the motor for the testing, I actually used some scrap bits of wire to make up the difference so that this motor isn't being penalized by the extra weight of that MR30 connector. This motor from Axis Flying, the Speedy Pizza Drone's Diavola motor, is another example of a two-piece bell design. But other than that, all of the features of this motor are quite similar to the T-motor and the 533, apart from the bearing in the bottom of the motor is not recessed as deeply into this motor as with the 533. If we come over and look at the RC Power motors, we have the GTS V4, and again this has a unibell design, but otherwise the features are pretty similar to all the other motors. And we have the RC Power Wasp Major, which is the current best performing motor in my motor testing. And it's a bit of an interesting size. This is a 22.6 by 6.5 millimeter motor. So that's a really interesting size, a bit different from everything else we've got on test. We'll have to see how this performs against the best of the best racing motors. And then we also have this RC Power GTS V3. This is a 2107.5. Yeah, 2107.5 size. So this is a bit narrower and a bit taller than the other motors that are on test. So we can see how that plays into things like motor responsiveness. Now that we've looked at the motors on the bench, we're going to have a look at the test results. Now, to save time, I'm not going to recap all of the motor testing procedures and methods that I used to get this data, but I am going to put a link down in the video description to a previous motor testing video where I do cover all of that in a lot more detail. So if you're interested to know exactly how I put these motors through their paces, then you know where to go. But for now, let's get on to looking at the results. Let's start by looking at the thrust testing results. And thrust testing is kind of like the bench press of motor testing. It is important who puts up the biggest number, but that's not all there is to it. It's also important how that thrust is delivered and how efficiently the motor is able to generate that thrust. A lot of manufacturers will talk about the linearity of throttle response when they talk about thrust. And this is essentially meaningless. It's just marketing fluff. As you can see, all of the motors that I've tested have a very similar shape to the curve of throttle versus thrust. We see that there's a bit of a curve at low throttle, and then the motors get pretty linear at higher throttles above 50% or so. And this is typical not just of racing motors and not just of motors of this size. This is typical for all motors. So when manufacturers talk about a motor being more linear than another motor, I mean, basically all motors are equally linear in my opinion. So I don't put a lot of faith in motor linearity. When it comes to delivering thrust smoothly, we have to look at the F40 Pro 5 2150 kV here. So this is a relatively small motor, 2306. It's got a huge kV, and you can see that it really struggles a bit to deliver power smoothly at that high throttle position. And so that's something to be aware of when you're picking a motor that's small with high kV. It will deliver a lot of thrust, but it's not going to be very smooth doing it. And that might make it slightly more difficult to control that throttle, particularly when you're up in that 80, 90 or close to 100% throttle range. Let's take a look at the thrust test results in this table format so we can see how the motors stack up against each other. To help compare them, I've also included the measured kV. Now, to measure the kV, I've run the motor at full throttle at 10 volts without a prop on it, and then divided that by 10 to give the measured kV. And because the test is the same for every motor, those results are directly comparable. You can see that for some motors, there's quite a bit of difference between the measured kV and the nominal kV that the manufacturer states for the motor. It can be 50 to even 100 kV sometimes. The motor that delivered the most thrust here is the T-Motor F40 Pro 5, but that 2150 kV meant that it took 48 amps to deliver that thrust number, and it got super hot doing it, even just a short test. So I don't think I could recommend such a high kV motor for racing. I think it's just going to get far too hot and drain the battery far too quickly to be a really excellent racing motor. Probably something like 1950 kV on 6S is going to be better for the F40. The next graph we're going to look at is the motor efficiency graph. And what I want to draw your attention to here is two things. The first is that the efficiency of a motor decreases as you increase the throttle. So the motor gets less efficient the more power it's trying to make in general. And also that the rank order of motor efficiency, so which motors are more efficient or less efficient, typically don't change across throttle. So the most efficient motor at a lower throttle position tends to stay the most efficient as you move to higher throttle. And what we can see also is that it tends to be the lower kV motors that are more efficient and higher kV motors are less efficient. Although that's not always true, and we are going to talk about one very key upset here. Let's take a look at the table of efficiencies now. And we're taking the efficiency at 1,000 grams of thrust. And as we saw from the previous chart, the rank order of efficiency at 1,000 grams of thrust is really representative of the rank order of efficiencies over the whole throttle range. what we can see is that the RC Power Wasp Major and GTS V3 really stand out here as having exceptional efficiencies, particularly given the amount of thrust that they generate. Normally we would expect lower kV motors to be more efficient, and therefore you'd sacrifice some top-end thrust for efficiency. But these RC Power motors find a way to be efficient and very powerful all at the same time. I've done hundreds of finite element motor simulations to try and figure out what makes the RC Power Wasp Major and GTS V3 so efficient. And it's thrown up some things that I don't think anyone in the community has talked about before. If you're interested to know what makes those motors so good, make sure you're subscribed and hit that notification bell so that you see that deep dive video as soon as it's available. The next chart we're going to look at is the flywheel test. And this is where we use the motor to accelerate a flywheel from 5,000 to 20,000 RPM as fast as we can. And this tells us the maximum torque that the motor is able to generate at every RPM between 5,000 and 20,000. And this is really interesting to see the capability of the motor to accelerate a mass, the amount of torque that it can generate, and that's going to directly tie into motor performance and motor responsiveness. What we can see here is that the RC Power Wasp Major motors are able to deliver the maximum amount of torque. That occurs at about 7,500 RPM, and they're able to generate about 0.27, 0.28 Newton meters of torque. At high RPMs, again, we see that F40 Pro 2150 kV coming in. That really high kV allows it to continue to generate a lot of torque at high RPMs. Obviously at the expense of massive current draw and massive heat. So that motor nearly smoked on this test. So something to be aware of is that it's not always great to just be able to put up a huge torque number if it requires an enormous amount of current and heat to do it. If we look at the table of torque values now, we can see that I'm taking the torque at 50% throttle and 10,000 RPM. 50% throttle chosen because that's the maximum throttle that I can run this test at without starting to smoke motors. And 10,000 RPM is chosen because that's after the torque hump that we see in the torque versus RPM graph. It's where the back EMF has built up to a level where it's starting to limit the current that the motor can draw. And so that's a good point to take, which is even across all the motors and not subject to exactly when the motor starts to pick up at the start of the test. The T-Motor F40, the RC Power Wasp Major and the 533 motor all deliver really good torque numbers at 10,000 RPM. And that speaks to the magnetic design of the motor. It's able to create a powerful field that can generate a lot of torque. And that bodes very well for motor responsiveness, which is what we're going to look at next. It's interesting to see that the T-Motor F60 performs much worse than the F40 in this test, despite being a larger motor. Typically you would expect a large motor to have more torque than a smaller motor, but there are a lot of factors that go into the design of a motor, like the thickness of the magnets and the flux ring, which can influence the maximum torque that the motor is able to develop. So sometimes we can't just go on the size of the motor alone. The final test we're going to look at is motor responsiveness. This is the acceleration that the motor is able to achieve stepping from 10% to 50% throttle with the test prop on it. So this is the HQ5 by 4.5 by 3. Obviously, a motor that can generate more torque is going to be able to accelerate the prop faster, but it's also to do with the inertia of the motor bell. A motor that's got a very heavy bell with a lot of inertia is going to be slower to accelerate up to a higher RPM. And motor responsiveness is really important for the handling of the quad. Whenever you're doing fast turns, fast movements, you need the prop to be able to change the thrust that it produces very, very quickly, and that's down to how responsive the motor is. We can see that the motors that are able to generate a lot of torque, the T-Motor F40, RC Power Wasp Major and the 533 motor all do really well in the responsiveness test as well, coming in the top half of the rankings. And that's to be expected. A motor that can generate a lot of torque is going to be able to accelerate that prop quickly. Where we see the order change a little bit, that's going to be down to the inertia of the motor. Motors with a lightweight bell will be able to be more responsive even if they don't generate so much torque. And so that's why it's good to have both measurements. You can see the torque value, which speaks to the magnetic design of the motor. You can also see the responsiveness value, which takes into account the motor inertia as well. Now let's look at the scores for all the tests in aggregate. And the way that I calculate a motor's score for a particular test is I take its performance in that test and then divide it by the average performance across all the motors I've tested in a similar size class. So if you see a score of 105, for example, that means that that motor delivers 5% more than the average performance for all 5-inch motors. And what we can see is that the T-Motor F40 Pro 2150 kV and the RCM Power Wasp Major, the Axis Flying Diavolo 2207 and the 533 motor all come out at the top of the list for total score. And that means that overall across all the tests, they performed on average the best. But there is one step further that we need to go, and that's we need to normalize this total score by the weight of the motor. Obviously, it's possible to make a motor that performs better by making the motor heavier. You can add more magnetic material, you can add more copper in the windings. All of that is going to improve the performance of the motor and its efficiency. So we normalize these scores by the weight of the motor to get the final ranking. Once we've normalized by weight, we have our final ranking. And up in S tier, we have the RCM Power Wasp Major. Both the 2020 kV and 1860 kV performed really well in my testing, especially when you normalize by the weight of the motor. They're around 10 to 11% better than an average 5-inch motor using this scoring system. Behind them in A tier, we have the Axis Flying Diavolo 2207 in 2020 kV, the RCM Power GTS V3 1980 kV, and the 533 Heads-Up 2207 motor as well. All of these motors perform really well, around 7 to 8% better than an average 5-inch motor across all the tests. Below them in B tier, we have the RCM Power GTS V4, both versions 1960 and 2030 kV, and the Axis Flying Diavolo 2207 1960 kV. And finally in C tier, we have the T-Motor F40 and F60 Pros. And the F40 at 2150 kV, although it performs really well, I think it's not efficient enough. It draws too much current and it gets too hot to be a really good racing motor. So I'm limiting myself to the slightly lower kV versions of the F40 and F60. And it's not that these motors perform badly by any means. They all perform better than average across all the tests that I've done. It's just that this is a very competitive stable of motors that I've put them up against. And so they're just not able to distinguish themselves against the competition in this particular set of tests. Whether you're an FPV racing pilot looking for a motor that's going to give you an edge over your competition this year, or just someone interested to stay up to date with the latest in drone motor technology, I hope you found this video interesting. If you're looking to learn more about some different products, then I'll put a link down in the video description to my website, AOS Labs. I collate all the test results from all the product testing that I do on motors, props, and video systems, and I put it all up there so that you can refer to it whenever you want to. There are also product recommendations so that you can make sure that you're spending your money on the right kit. If you like this work and would like to support more videos like this, I do have a Patreon and you can join from just a few dollars a month. It's going to give you access to a special area of my Discord server, sneak peeks at the products I'm working on, and even more in-depth test data. So if that's of interest to you, I'd really appreciate you checking it out. As I mentioned earlier, I am planning a deep dive on all the factors that affect drone motor performance. We are going to be looking at the materials and geometry of the stator and the rotor to figure out how we can make our motors perform even better. Now that video is going to rely on a lot of fundamental principles of electromagnetics, and if you want to brush up on those topics in advance, then our sponsor Brilliant has an offer for you. Brilliant.org is the best way to learn maths, science and computer science interactively. They have thousands of lessons on topics ranging from foundational mathematics all the way up to advanced AI, machine learning and data science courses, with new lessons being added every month. The course that I want to focus on today is electromagnetics. The science of electromagnetics governs the interactions between electric and magnetic fields and also describes how electric current in wires can create magnetic force. It's these fundamental laws that allow our motors to convert electrical energy from the battery into mechanical power to drive a propeller and create thrust. If you understand these principles, not only will you be able to make the most out of the motor test results that we've gathered so far, but also you'll be perfectly positioned to understand everything that I'm going to cover in my deep dive on FPV motor performance. To support us, Brilliant is offering a free 30-day trial of everything they have to offer. To take advantage, visit brilliant.org/chrisrosser or click the link in the video description. The first 200 of you will also receive 20% off an annual subscription to Brilliant. 30 days is plenty of time to complete the electromagnetics course, so if that's what you're interested in, it needn't cost you a penny. I'd love to get your feedback on this latest round of motor testing, so please leave your thoughts down in the comments. That's all I have for you for today, so until next time, I wish you all very, very happy flying.